Hello and welcome to Get to Know Science. In this video we'll be looking at series and parallel circuits and how we should treat current, potential difference and resistance in them. We'll have a look at a question which you may face in an exam, and then we'll solve it using the principles that you'll learn in this video. So first we need to define what a series and a parallel circuit is. So here they are. This is a series circuit. It only has one loop and all the components are in the same loop. So these two lamps are in series with each other. A parallel circuit has more than one loop. So that's one, that's the second. The two lamps are on separate loops, so they are in parallel to each other. And for each type of circuit, you need to know what happens with the current, the potential difference, and the resistance. We'll start with the series circuit. The first thing to understand with a series circuit is that the current I is the same at any point in the circuit. So if we have 2 amps measured here, we will have 2 amps here, and we'll have 2 amps here as well. Everywhere in this circuit the current will be 2 amps. The reason is because the current is the flow of charge. In this case the electrons are the charge carriers, and we can't create or destroy electrons, and the electrons have nowhere to go except this one path. There is only one path for them to follow. So there will be the same flow of electrons anywhere in the circuit. So we can say that for a series circuit the current is the same all the way around this circuit. The potential difference, or V, the voltage in a series circuit, is shared among the components. The total potential difference, or the total joules per coulomb, comes from the battery. And the potential difference across each component depends on its resistance. So if we have a look at lamp 1, the 5 ohm lamp, this is a lamp with a resistance of 5 ohms. Now we know that V equals IR, so that's Ohm's law. The voltage or potential difference is the current times the resistance. So that means that for that lamp, the voltage or the potential difference across it is 2 amps multiplied by 5 ohms, which gives us 10 volts across this lamp here. If we look at the second lamp, V is equal to IR, I is still 2, and R is now 1. So 2 times 1 equals 2 volts. So there's 2 volts of potential difference across this lamp and 10 volts across this lamp. So do you notice that the two voltages across these two lamps, 10 and 2, adds up to the voltage of the battery, which is 12 volts. So we can say that the voltage from the battery is shared amongst the components in series. So voltage is shared. Now we have to look at resistance. So to find the total resistance in this circuit, all we have to do is add up the resistances of all the components that are in series with each other. So R total would equal R1 plus R2, in this case this resistance and that resistance. So in this case it would be 5 ohms plus 1 ohm, and that gives us 6 ohms total resistance in this circuit. And if you notice how if V equals IR for this total circuit, the total voltage which comes from the battery, V total, multiplied by the the total voltage in this circuit which comes from the battery, 12 volts, equals the current, which is 2 amps, multiplied by the total resistance, which is 6 ohms. Okay, so if we treat all the resistances as one block of resistance, we can do V equals IR, and we see that it still works. So the voltage from the battery, using the current in the circuit and then taking the total resistance together, will still work, and V still equals IR. So that's how we treat current, potential difference and resistance in series. So that's how we treat current, potential difference or voltage and resistance in series. Next, let's look at the parallel circuit. So if we look at this parallel circuit and we take the current first, we see that it can't be the same everywhere like it was before in the series circuit. If we trace the way the current travels through this circuit, or rather the electrons, how they travel, they go from negative to positive, so they go around this way, and then at this junction they have to split. Some of them will go this way, some of them will go that way. Most of the current will go this way because it's the path of least resistance. There's only 3 ohms of resistance here versus 6 ohms in this branch or in this loop. So you'll get more current going through this lamp than you will going through this lamp. And the total current, 6 amps, will be split along both of these branches. So if we label this I1 and I2, we know that the total current, 6 amps, is equal to I1 plus I2. And if there were more branches, then you'd have plus I3 plus I4, etc., etc. So I1 will be bigger than I2 because there's less resistance there. Then as they travel this way and this way, so the current will go around this loop and the current will go through here, and they'll rejoin at this junction. So here we'll have our 6 amps again. Okay, so now let's look at the voltage or the potential difference across each lamp. The potential difference across each of the lamps is 12 volts. And this is because the energy per unit charge is the same. So you'll have 12 volts across here, and you'll have 12 volts across that lamp there. So the energy per unit charge is the same. There may be a different number of charges in each branch because some of the current goes this way and some of the current goes that way, but the amount of energy per unit charge, aka the voltage, is still the same. It's still 12 volts, or still 12 joules per coulomb in each branch. The number of coulombs might have changed, but the joules per coulomb hasn't changed. So we can say in a parallel circuit, the voltage across each branch is the same in parallel. So finally, let's look at resistance. Now, if you're doing your GCSEs, you won't be asked to calculate the total resistance in a parallel circuit. That's more of an A-level thing. But you do need to know that the total resistance is smaller than the smallest resistor. So looking at our circuit, the smallest resistor is the 3 ohm lamp. Therefore, the total resistance is going to be less than 3 ohms. Now let's try to make sense of this because it's quite difficult to understand. Imagine we have 4 amps. So I1 is 4 amps. We have 4 amps flowing through the smallest resistor. That's the highest current in either of the 2 branches, because if that is 4 amps, then I2 has to be 2 amps, right? Because 6 would be 4 plus 2. So that's the highest current in either of the 2 branches here at this junction. But we know that the total current is higher than 4 amps. So therefore the total resistance must be lower than 3 ohms. If we take the total resistance as the resistance of this entire section with the two lamps included. So if we pretend that all of the lamps are in a black box, and we want to know the total resistance of the black box, we can do this. We know that V equals the total current multiplied by the total resistance. So if we rearrange, the total resistance is the voltage from the battery divided by the total current. So that's 12 volts divided by 6 amps, which means that the total resistance is only 2 ohms, and that's smaller than the smallest resistor we had in the parallel circuit. So we can see that the total resistance is always smaller than the smallest resistor in a parallel circuit. Okay, so the total resistance is smaller than the smallest resistor. So to recap, let's go back to the start. We need to know the difference between a series circuit and a parallel circuit, and we explained that earlier in the video. If we have a look at the series circuits, there are 3 rules that we need to know when it comes to series circuits. We need to know that the current is the same anywhere in the circuit. We need to know that the voltage is shared among the components that are in series, and we need to know that the total resistance, we just add up the resistances in the circuit. Moving on to a parallel circuit, we know that the current will split at a junction and that the total current is equal to the sum of the individual currents that split off. We also know that the voltage is the same across any of these components in a parallel circuit, and that the total resistance is going to be smaller than the smallest resistor. So now let's try a question to test if we've understood this. So here's a question. Here's a circuit. We have a 9-volt battery. This is a switch. We have a resistor R, which is in parallel to these 2 resistors here, which are in series with each other. So these 2 are in series with each other, but they're both in parallel to resistor R, and it's in parallel to the 9-volt battery. And we have a current of 0.5 amps traveling through this resistor R. Now notice the direction of the current, right? Normally we say the electrons move from negative to positive. So the electrons would be going the opposite way to this current. But this is what we call the conventional current. And for historical reasons, the conventional current is in the opposite direction to the electron flow. So you do need to remember that. Okay, so the first question here says, what is the potential difference between A and B? Well, this is a parallel circuit. So we know that the voltage of the battery is 9 volts. Therefore, we know that the voltage across R is 9 volts. And therefore, we know that the voltage across the combination of these 2 resistors has to be 9 volts as well. So the potential difference between A and B has to be 9 volts. Okay, the potential difference across the 15 ohm resistor is 5 volts. So for this one, 5 volts across that one, between here and here. What is the potential difference across the 12 ohm resistor? Well, if the total from A to B is 9 volts, and we know there's 5 volts across this one, then there must be 4 volts across the 12 ohm resistor to make up 9. Because resistors in series, these 2 are in series, and the voltages will add to give the total voltage between A and B, which is 9 volts. So it has to be 4 volts to add to 5 to give you 9. Okay, part B. Calculate the combined resistance of the 12 ohm and the 15 ohm resistors in series. Okay, so we have an equation for this. The total resistance, or the combined resistance, is equal to R1 plus R2. In this case, we have a 12 ohm resistor and a 15 ohm resistor, and if we add those together we find that the total resistance of this series combination of resistors is 27 ohms. So we can write the answer here, 27 ohms. Okay, B part 2, calculate the current that flows through the circuit at X. So X is here. What current flows through this circuit? Well, we've just found the combined resistance of these two resistors. So we have R. We want to find the current, which is I, and we have the voltage, which is V, 9 volts. We know that V equals I times R. That's Ohm's law once again. And we want I. So I is going to be equal to V divided by R if we rearrange this equation to give I. So our V is 9 volts and we're dividing that by 27 ohms. That's 1 over 3, which means 0.33 amps traveling through point X. So the current that flows through the circuit at X, 0.33 amps. Okay, calculate the current flowing through the circuit at Y. So Y is here. That's the total current before it splits. Y is the total current. So the sum of the current in this branch here and in this branch here. So we know that at X we've got 0.33 amps, and we know that traveling through the resistor R we have 0.5 amps. So total current is equal to the sum of the currents in each branch. So we know it's 0.5 amps plus 0.33 amps, which gives us 0.83 amps traveling through Y. Okay, and lastly, calculate the resistance of the resistor labeled R. So this is resistor R. What do we know about this resistor? Well, we know that there's a current of 0.5 amps traveling through it. We know that the potential difference across this resistor is equal to 9 volts because it's in series, it's in parallel. So we know that the resistance is going to be equal to, again, Ohm's law. If we rearrange it for resistance, we get V divided by I. We know that V is going to be 9 volts because it's in parallel with the battery, and we know that I is 0.5 amps. So that gives us 18 ohms of resistance for resistor R. That was the rules of series and parallel circuits, how we treat them. We've got to treat them differently because they're different situations. You've got to know the rules regarding the current, the voltage and the resistance in each of those types of circuits, and we've just showed you how to apply it to this question in order to find these answers. So I hope that video was helpful. If you have any suggestions, comment below. Otherwise, like and subscribe, and I'll see you next time. Thanks for watching.